This is the last lesson, and then we will be doing review tomorrow and Wednesday, and then you'll have your test on Thursday.
Oh shit! I don't even remember what we were doing.
So you're going to want to go back and look at all of that. So it'd be like the graphing polynomials, dividing polynomials, stuff like that. But you're definitely going to want to go back and look at that and complete the review that's already on Canvas.
Oh, word?
Huh?
I said, oh, word?
Yeah. It's okay. Review is not due until you take the test on Thursday, technically. So you have plenty of time.
I'm trying to explain to Jonah how to get on here.
You just have to click the thingy.
Yeah, I know.
I tried to make it as easy as possible. We'll give them a chance, I guess, to come on.
Dude's clueless.
How was everyone's fall break?
It was all right.
It was all right. Do anything fun?
No, not really. I can't really do anything fun anymore, so.
Zach, come on. There's a fun thing to do.
I can't. My life has been boring.
Well, I hope it gets better.
It will.
Did Jonah figure out how to get on yet?
I don't know. I told him.
Okay. I guess we'll just go ahead and, oh, there we go. Now we can go ahead and start technically. Okay, so a rational function is simply the quotient of two polynomial functions, so the things that we've been looking at. But something unique that happens with rational functions is that they allow for places where our graph doesn't actually exist, and we call those asymptotes. I know it sounds like a cuss word, but it's not. So we can have two different types of asymptotes. We can have a vertical asymptote, or we can have a horizontal asymptote. A vertical asymptote occurs when our denominator equals 0. And in case you can't remember what a denominator is, it's the bottom part of a fraction. We use a dotted line, a dotted vertical line, to indicate a vertical asymptote on a graph. And then we use a dotted line going horizontal to indicate a horizontal one on a graph. A horizontal asymptote is where the graph evens out as x values go to negative infinity or infinity. I know that sounds super duper confusing. We can also think of horizontal asymptotes as the end behavior of my graph. So all that we are going to do in this lesson is we are going to identify where horizontal and vertical asymptotes occur. And then we're going to identify domain and range of the functions as well. Okay. So hopefully you all have this written. Does anybody not have it written? Okay. So it is also in the notes, and I will post this video to Canvas at the end after it uploads to my Google Drive. So we're just going to practice finding our asymptotes. You will not have to graph on today's homework, even though the homework does say to graph. Don't do it. We're just finding the asymptotes here. Our first example is the rational function x plus 1 over 2x minus 4. On this, in case you can't remember, the x plus 1 is our numerator because it's in the top part of our fraction. And the 2x minus 4 is our denominator because it's in the bottom part of our fraction. I can go ahead and identify my vertical asymptote, which I'm just going to abbreviate as VA. Remember, our vertical asymptote occurs when our denominator equals 0. So I need to take that denominator of the fraction, and I need to set it equal to 0 and solve for x. So I'm going to go ahead and add the 4 across, and then divide by 2. And this means I have a vertical asymptote at x equals 2. On a graph, let's say theoretically I have been graphing this. This means I would go to the x value of positive 2, and I would draw a dotted line. A vertical asymptote is a dotted line that can never be crossed. So no matter what happens on each side, my graph is never going to cross over. Okay, so it's always going to have a split there. As it turns out, if you were to graph this, which again, I'm not telling you you need to do. Let me draw some more lines on here. If we were to graph this, it would look something like this. So it's really easy to tell where the vertical asymptote is, first because we calculated it, and second because it's that dotted line where my graph splits and goes different directions. But this also has a horizontal asymptote, which is a little bit harder to identify. So when I'm talking about horizontal asymptotes, I like to think about a horizontal line that my graph just kind of creeps up to and gets really, really close to, but never actually gets to. So if I'm looking at just the right side of this graph, is my graph evening out somewhere, or is it going infinitely down to negative infinity? What do you guys think?
Infinitely.
Infinitely? So it doesn't look like it's evening out, like right here. Doesn't it kind of look like it's starting to even out as it gets closer and closer to that?
Oh, okay, yeah.
Yeah, so that is actually a horizontal asymptote. And the really cool thing about that is that it also occurs on the other side of my graph. This doesn't always happen, but here it did. So I have a horizontal asymptote at y equals 1 because both sides of my graph started to even out or level out as I approached y equals 1. It is possible that the right side of your graph and the left side of your graph will have different horizontal asymptotes. That's perfectly fine. In fact, there could be like 4 horizontal asymptotes in a graph. That's not a big deal. It is also possible to have more than one vertical asymptote as well. The interesting thing is that technically we can cross a horizontal asymptote. So the graph could have gone above it and then evened out later on. We can never cross a vertical though. Okay, so make sure you keep those straight. Is everybody done drawing this one? And writing it? So the way you're going to do it on your homework is you would say vertical asymptote at x equals 2 and horizontal asymptote at y equals 1. So let's keep going. I'm going to draw another one for you, and you're going to identify any vertical or horizontal asymptotes that occur. So this one is the rational function y equals -2 over x plus 3, and that's all minus 1. And when I draw the graph, this is kind of what our graph is looking like. Give me a second. Okay, so I want you to draw this graph, and then I would like you to identify any vertical asymptote that's occurring, and then any horizontal asymptote that's occurring. I'll give you guys a couple minutes. Right now, 4 out of 7, so that's not terrible.
Really? Have you had kids come in all day?
They've been good. It might not pause because.
I'm not pausing.
Okay.
I would just
Oh, looks like I
it's 6.
Is that Mr. Booker?
got.
What's up, buddy?
What's up, Mr. Rose?
Not much. Just doing a little bit of math.
Are you learning anything?
I'm trying my best, okay?
That's all I can ask for, Zach. That's all I can ask for. Keep it up. That's good.
I will.
Yeah. Actually, pretty good. Pretty good. Okay, I'll give you guys another minute, and then we're going to call on probably Mr. Rose to start us off.
Oh, no.
Zach.
Hey, can you move the camera over a little bit? Is there any
which
other
direction?
line on the graph? There we go.
That better? Okay.
Yeah.
Yeah, just
Okay.
always let me know if you can't see something, because I don't know what you see versus what I see. Again, I would like to identify my vertical asymptote and then my horizontal asymptote or totes, depending on if there's one or more.
I think I got both of them.
Think you got both? Okay, Zach, start us off. What's our vertical asymptote?
-3.
X or Y?
It'd be X, wouldn't it?
Yes, because it goes through my x-axis. So I have the vertical asymptote at x equals a -3. Perfect. Did anybody find a different vertical asymptote? Okay, what about a horizontal? Let's go with, Boone. Maybe.
You can do it, buddy.
Elijah. He says -1. Do we agree with that?
I put -1 also.
Good. -1 is in fact our horizontal asymptote, and it's true for both sides of my graph, because I can clearly see that both parts of my graph are leveling out as I get closer and closer to y equals -1. Make sure when you're talking about horizontal asymptotes, it's always y equals something, and vertical is always x equals. Are there any questions about identifying a vertical and horizontal asymptote from a graph?
No.
We're doing pretty
gonna
good.
have to, like, draw the graphs.
You will not have to
on the
draw the graph.
homework, but eventually.
Not actually, no, not at all.
Sweet.
Not for these ones, because they get really, really confusing.
Yeah.
So I do that for honors. I don't necessarily do that for you guys.
Haha.
Okay, I'm going to give you one more, and I would like you to do this one completely on your own, like the other one. I'm gonna make it a little different for you this time. Okay, so here is your graph. I would like you to identify any and all vertical asymptotes and any and all horizontal asymptotes. Move it over so you can see it a little bit better. And I give you guys a minute to do that.
What's the y equals x squared plus 4 over x squared minus 4?
That is our rational function. This is the graph of that.
Oh, okay.
Yeah, so I give you both the function and the graph.
Okay. Jonah, how you doing? Are you lost?
No, I'm good.
Sweet.
Okay, Jonah, why don't you tell us what a vertical asymptote is or are?
All right, so for vertical, I got -2 and 2
Okay, how did you get -2 and 2?
because on the top left thing, it's like pointing up and it's like veering towards the -2, and on the bottom, it's going down and it's going towards the -2,
Okay,
like vice versa on the other side.
right. So my graph is splitting at those x values.
Yeah.
So I have a vertical at x equals -2 and a vertical at x equals 2.
Yep.
I like it. Anybody have something different? Fantastic. So Devin, I would like you to tell me what all of my horizontal asymptotes are. Okay, so Devin says y equals 1. He said that's the only one I've got. Do we agree with that?
Think so.
We should, because it only pertains to the end behavior of my graph. So this part here in the middle, it doesn't matter where the top of that parabola is going to be. It only matters as I go to infinity or negative infinity. So y equals 1 is my horizontal asymptote. Good job. Anybody super confused when you have a graph finding your asymptotes from that? Okay. So now let's move on into domain and range temporarily, because they kind of pertain to our asymptotes as well. Okay, so our domain for any function is the list of all possible x values that could be plugged into it. Whereas our range is a list of all the possible answers or y values we can get out of it. For each of these, we assume that our domain is -infinity to infinity, and that our range is -infinity to infinity, because we assume it's going to work for everything. But that's not always true, right? Because you just, on this example up here, showed me that we had gaps in our domain and our range. Our gaps in the domain were our vertical asymptotes. The gap in our range was our horizontal asymptote. So these are called the exceptions to our domain and our range. So our domain is all possible x values except vertical asymptotes. And our range is all possible y values except our horizontal asymptotes. So what I want to do now is I would like to go back up to this graph that we just looked at, and I would like to identify the domain and the range for that graph. That's going to be my goal here. So I'm going to go ahead and move this over. Hopefully you all have the range and stuff written. Maybe not.
I'm good.
Okay. So as I'm looking at this graph, I would like to identify my domain, and I would like to identify my range. Sometimes it's easier to find the numbers that don't work rather than all the numbers that do work. So as I'm looking at the domain, remember those are just our x values. So from left to right, did I have any gaps or any asymptotes that occurred for those x values? Yeah, I had two. I had a gap at -2 and a gap at +2. So there are two ways that I could write this. The first way is I could say that my domain is all x, except x cannot equal -2 and it cannot equal 2. That's one way of writing our domain. I don't really like that way as much for you guys because I don't think you really process or understand what it means.
Nope.
The other way we can write it is we could do -infinity to infinity, breaking at those asymptotes. So I would do -infinity to -2, union, -2 to 2, union, 2 to infinity.
Oh my gosh.
And then that would be my domain. Either one of these are acceptable answers. Our range then works the exact same way. So again, I'm looking at the exceptions for my range or for my y values. So clearly, I have a gap right here at my horizontal asymptote. I actually have a gap going from my horizontal all the way down to the top of that parabola. So I'm going to have a big gap in my domain, in my range, sorry. So I'm going to say that my range is -infinity to -1 because that's where the top of my parabola is, union, and then 1 up to infinity. Because I had to show that there was a gap in there. If I didn't have the parabola and I just had that horizontal asymptote happening, then I would have written it more like this one, where I had just a gap at that number instead of a huge gap, like we did here. So pretty much your domain is every number except your vertical asymptotes. And for the most part, your range is every y except for your horizontal asymptotes. I don't believe you'll have one like this on your homework. I'm about to make it a little bit more complicated because, you know, I love to do that. And I'm going to tell you that we are no longer just limited to vertical and horizontal asymptotes. It's also possible that we have an oblique asymptote. An oblique asymptote, then, So here is a rational function that's going to have an oblique asymptote. And when I graph it, this is what an oblique looks like. Jeez, if I can draw this. It is literally a diagonal asymptote. That's what oblique means. Which means I can't just write the equation for that asymptote as x equals or y equals some number. It's going to actually be some line. So it's going to look like y equals mx plus b, kind of. But it's kind of hard to just eyeball it and figure out what that equation is going to be. So there is a shortcut to finding your oblique asymptotes. And that is using synthetic division. We've come full circle. So in order to find the equation for this asymptote right here, I need to take this x squared plus 4x plus 6, and I need to divide it by x plus 1. I'm going to use synthetic division when I do that. So I pull down my coefficients. I do my nice little grid. I'm going to be dividing out -1 because I take the x plus 1 and I set it equal to 0. And I solve for x. And then I do the synthetic division just like I did before. Drop down that first number, multiply. And that's what I get. Everyone remember synthetic division?
Kinda.
Kinda, okay. This is the really, really cool part. So once I have found this quotient right here, remember, our last number is the remainder. The number before that is our constant. And the number before that is our x. So I could write this as x plus 3 plus that remainder of 3 over x plus 1. Right? We did this a long time ago. My oblique asymptote is going to be everything except that remainder. So just like we did before, OA stands for oblique asymptote. And this is occurring at y equals x plus 3. So that is literally the equation for that line. And then you're done. How are we feeling?
You know, just
We're almost done.
yeah.
Okay, so we have horizontal asymptotes, we have vertical asymptotes, and we have oblique asymptotes. There is another type of gap that we could have in a graph, and that is called a removable discontinuity. And on a graph, a removable discontinuity is simply a circle. So it's literally just a hole in the graph. So here's an example. And then here's what the graph would look like. Let's see if I can do this. Not going well. There we go. Okay, so on this graph, I can clearly see that there's a vertical asymptote, and I can clearly see that there's a horizontal asymptote, but there's also this hole right here. That is our removable discontinuity.
There's a hole? Like
It's a hole. It's just an open circle in my graph.
Oh my god.
This happens when the numerator and the denominator share a factor. Okay, so in order to find this removable discontinuity, I need to factor the numerator and I need to factor the denominator. So when I factor the numerator, I want two numbers that multiply together to get 6 and add to get 5. Well, that's clearly going to be 3 and 2. In my denominator, x squared minus 4 means I'm looking for two numbers that multiply to get a negative 4 and add to get a 0. And that's going to be x plus 2 and x minus 2. Once we've factored, what do we notice? Say it again, Devin. I guess I can just go to the messages and find it. The x plus 2 cancels. So my numerator has an x plus 2, and my denominator has an x plus 2. So in order to identify that removable discontinuity, I take that factor that they shared, and I set it equal to 0, and I solve for x. So I have a removable discontinuity, or RD, at x equals negative 2. That is not the end of class. And I did, in fact, have a removable, or a hole, at x equals negative 2. So that is the end of all of our different types of asymptotes and discontinuities. So you have the vertical, which is where the denominator equals 0. You have the horizontal, which is the end behavior of the graph, what it evens out to. You have the oblique, which is a diagonal line that can occur on the graph. And then you have a removable discontinuity, which is a hole in the graph. Those are the only 4 things that you need to worry about, plus domain and range, of course. So I have a follow-up question for you. If I didn't have the graph, could I find a horizontal asymptote or an oblique asymptote? Do you guys think we could do that? Yes. Devin, how do you think we could do that? Do we have an idea, or are you just saying it is possible? Okay. It is 100% possible to find these asymptotes without a graph. And it is based solely off of the degree of my numerator and the degree of my denominator. I know you thought we were done with that, but we are not. Okay. So let's do a nice little recap, and then we'll get into how to find those things. Okay, so this is a removable discontinuity. We're going to rehash that one first. A removable discontinuity is found by identifying the factors of our numerator and the factors of our denominator. That are the same. So I need to factor both of them, and I look for something that they have in common. So a factor that they both contain. I set that factor equal to 0 to find my removable discontinuity. Then we have our vertical asymptotes. I think this one is the easiest to figure out. Because we just set the denominator equal to 0. And solve, of course. we always check for our removable first. Once we take out whatever they have in common, then we check for our vertical. Okay, so our vertical asymptote is never a factor that's shared with our numerator because that's a removable, and once it's removed, this is what we do next. Okay, after the removable and the vertical, we can go ahead and test for our horizontal and oblique asymptotes. It is important to note that both of these, the removable and the vertical, are exceptions to our domain. So these are numbers that are not included in our domain. In order to do our horizontal and our oblique, we need to use some variables. So I'm going to say m is the degree of the numerator. And n is the degree of the denominator. If m is bigger than n, so if the degree of the numerator is bigger than the degree of the denominator, the horizontal asymptote m is smaller, sorry, will be y equals 0. So if the degree of our numerator is smaller than the degree of our denominator, the horizontal asymptote will be y equals 0. If they are the same, then the horizontal asymptote will be the coefficients on the leading terms. I know that sounds confusing, but once we get into it, it's not that bad. And then the third one happens when the degree of the numerator is larger than the degree of the denominator. There will be no horizontal asymptote, but there will be an oblique. And we find that using our synthetic division. So what we're going to do now is we're going to do 3 examples exactly like you will do them on your homework. Yes, this one was just a recap, Devin, except for this part. This part was new. Is anybody still, I guess I should give you guys a second because I'm assuming some of you are still writing. Okay, let's go ahead and start with an example. On all of these examples, I would like to identify all asymptotes and discontinuities. As well as domain and range. First one. of x equals x minus 8 over 2x plus 1. This f of x is no different than having a y there. It's just a different notation. Okay, so I like to go in a specific order. The first thing I'd like to look for is a removable discontinuity. So in order to find that removable, the first thing I need to do is I need to factor my numerator and my denominator. But on this one, they're not quadratics, right? There's no exponent on these x's, which means I don't need to factor them because they're technically already factored. So as I'm looking at these two are clearly not the same. So there is no removable discontinuity. You can cross it out or you could just put none. After the removable, I like to move into, what do you mean the camera is off from the board?
Just move it a little bit, like, toward you. Yeah.
There, okay, sorry. Fantastic. Okay, so again, the removable discontinuity does not exist because I didn't have any x squares anywhere. Okay. After the removable, I move on to my vertical. Vertical only exists when what goes to 0 or equals 0. Is it the numerator or the denominator? Come on, guys. Nope, denominator. A vertical asymptote exists when my denominator equals 0. So I'm going to take that 2x plus 1. I'm going to set it equal to 0, and I'm going to solve for x. First thing I do is subtract 1 over, and then I divide by 2. And I get a vertical asymptote at x equals negative 1/2. After the vertical, I go ahead and I move into my horizontal asymptote. I will either have a horizontal or I will have an oblique. I will never have both. Okay? So when we look for horizontal or oblique, I need to check the degree of my numerator and the degree of my denominator. So again, those are the highest exponents. What's the degree of my numerator? Well, what's the, yes, Devin, the degree on my x, or the exponent on my x, is a 1. So this is a degree 1. Same thing in my denominator. There is no exponent attached to my x. So that one is also a degree 1. Since both of my degrees are the same, this rule right here says that my horizontal asymptote will be the coefficients on the leading terms of my rational function. So my horizontal asymptote is going to be whatever numbers in front of x over whatever numbers in front of x in the denominator. So my horizontal is at y equals 1 over 2. Since there was nothing in front of the x, I assume it's a 1. And then my denominator had a 2 in it. So it's just whatever number is in front of that leading variable. And since there was a horizontal, there is no oblique. The last thing I need to do after I've done that is I need to identify my domain and my range. Domain, again, we assume is negative infinity to infinity, except for our removable discontinuities and our vertical asymptotes. I only had a vertical asymptote. I didn't have a removable discontinuity. So I would say this is negative infinity to negative 1/2, u negative 1/2 to infinity. So my interval needs to break at whatever my asymptote or discontinuities are. The same thing is going to apply for my range. I assume it's negative infinity to infinity, except for my horizontal asymptote. So I say negative infinity to 1/2, u 1/2 to infinity. How you doing, Devin? Not bad, okay. Truthfully, how do we feel about having to do this on your homework?
Absolutely terrible.
Absolutely terrible.
The domain and range is just throwing me off.
This is not really a huge part of it. I'm more interested that you can do this stuff up here. And if you can say everything except this, I would probably still count that.
Oh, okay.
So you don't necessarily have to write it as an interval like this. This is just the preferred way.
Yeah, because I don't understand any of that.
Okay. But are you okay with this part?
Yeah.
Okay. So this is the more important part, so we'll come back to this part. I do want to do another example. That way, at least try to get through one more example. And then I want you to finish looking at the notes and the other examples that are present. Okay? So this is probably the last one we're going to get to just because of time. Keep forgetting you guys can't see the whole thing. So my numerator is 2x squared plus x. My denominator is 2x squared minus 9x minus 5. And I'm going to make the list of the things I'm going to check for, starting with the removable discontinuity, then the vertical asymptote, then the horizontal asymptote, and then the oblique asymptote. I like to start with my removable discontinuity. What am I looking for when I'm looking for that removable discontinuity? Devin can't answer and Zach can't answer. So somebody else, how do I find that removable discontinuity? You can type it, you can say it, whatever. Don't make me call on somebody, because I will. Let's go ahead and do Jonah. Do I need to leave my numerator and denominator the way they are, or do I need to do something to them?
Don't you have to like put them like in parentheses or something?
I need to factor them, yeah.
Yeah.
Okay, so in order to find the removable, I need to factor. What can I take out of both of these terms? Hopefully you see I can take an x out. And when I do, I'm left with 2x plus 1. And that's my factored numerator. In my denominator, it's a little bit different. I'm going to go ahead and factor it for you. When I factor it, it becomes 2x plus 1 and x minus 5. What do I notice about that numerator and denominator, Stephen? See if Stephen answers.
Oh, I didn't know you called out my name. What was the question?
What do I notice about the numerator and the denominator?
Is that they both have the 2x plus 1?
Right, so that is my removable discontinuity. So I need to take that 2x plus 1, and I need to set it equal to 0. When I do that, I solve for x, and I get x is equal to negative 1/2. So that is my removable discontinuity. Which means if I were to be graphing this, I would have a hole or an open circle in my graph. Then to find my vertical asymptote, I take what's left in my denominator after I canceled out that factor. Yes, at negative 1/2. After I've canceled out that 2x plus 1 that they had in common, I have an x minus 5 still left in my denominator. So that's what I'm going to set equal to 0 now to solve for my vertical asymptote. So I have a vertical asymptote at x equals 5. So anything that exists in my denominator is either a removable discontinuity or a vertical asymptote. Then I just need to do my horizontal and my oblique. And to do that, we go back to the beginning, so the original rational function that we were given. And we need to pay attention to our numerator and denominator degrees. Well, the degree of my numerator is 2, because that's what my exponent is. The degree of my denominator, also 2. Since they are the same, that means that my horizontal asymptote is just that leading coefficient over the leading coefficient of the denominator. So this would be a horizontal asymptote at y equals 2 over 2, which reduces to y equals 1, which means there is no oblique asymptote. Okay, so this is what your homework is. It is identifying any asymptotes or discontinuities that you have, and then telling me the domain and range. For this one, our domain would be everything except negative 1/2 and 5, and our range would be everything except 1. You can always write it out like that too if it makes more sense. Okay?
So I can just put everything except.
You can put everything except. That's fine.
Really?
I will accept that, yes.
Oh, heck yeah.
Because you still know what you're talking about. You're just not writing it in a math way.
Dude, that just got a lot easier.
Okay, well, I will let you guys go, and I will post this video on Canvas in case you need to come back and look at it. And the notes are also on Canvas.
All right.
And so is your homework. So have a wonderful day, everyone.
Okay, see you later.
See ya. Thanks, Devin.